Can you guys see the screen?
Yes.
Okay. 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 Firstly, what we'll be doing is that we'll be training a simple perceptron on the OR logic. Okay. So the first step is that firstly we will be importing a NumPy library. So Python has these different libraries which are served for different functions. NumPy is particularly used for mathematical functions. Okay. So this library will help us perform all the mathematics because perceptron involves calculating the dot product, calculating the sigmoid function, or calculating a simple linear function, and so on. So the first step is just to import the NumPy library. Okay, so and then we run this program. Okay, so it will connect, and I think I will share this code as well with you guys so that you can do it along with me. Can I share it over here? Who is the class representative over here so that I can send the file to that person and they can forward it in your classroom? Anyone? Okay, I will just explain the code then. Okay, so the first step is import the NumPy library. Okay, so we have done that. Okay, now we have to implement OR logic on this simple perceptron, right? So the OR logic goes like when we have input 0, 0, the output is 0. For 0, 1, we have output 1. For 1, 0, it is 1, and for 1, 1, it is also 1. So this is the basic OR logic, right? So what we are doing here is using the Python programming language, we will be training a simple perceptron on the OR gate. Okay. How do we do that? So the step number one is that we will assign an array for the inputs and the outputs. Okay. So we say x np dot array 0 0. So we will use all this 0 0 0 1 1 0 1 1. So we say 0 0 0 1 1 0 and 1 1. Okay. And corresponding to that, we will have the output array. So y equals to np dot array 0 1 1 1. So 0 1 1 1. Okay. So this is a very simple step because we are training the perceptron on the OR logic. So we will initialize these two arrays. Okay. So this step is done. After that, we will initialize the weights and biases. Okay. So in case of simple perceptron, in case of simple perceptron, we will be initializing the weights with 0 and bias with 0. Okay. So here we say w equals to, so weight equals to np dot array, another array, which will initialize with 0. So w1 will be 0 and w2 will also be 0. All right. Then bias will also be initialized with 0. So this is the convention. Whenever we are training a simple perceptron, we will initialize both the weights and biases with 0. Okay. And then we will set a learning rate. So learning rate is something, uh, so it is basically, it will help us updating the weights and biases as we go on further in training the perceptron. Okay. So we can set the learning rate here. I have done it 0.1. You can do it 0.2, 0.3, 0.4, up to you. So here the learning rate we have set is 0.1. Okay. And then we run this. Okay. So our weights and biases have been initialized. We have set the learning rate. Okay. 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 Let me send it to you guys. Just give me a second. Okay. Okay. So I have sent both the codes with you guys. Okay. So okay. So you can do it along with me. Okay. So we have initialized the weights and biases, right? And I don't know if I have taught you guys earlier, but we use Google Colab for programming, all the programming. So you in your browser you can just search Google Colab and sign in with your Google account, and then you can open a new notebook, or you can just upload the notebook that I have shared with you guys. Okay. So all right. So we have initialized the weights and biases. Okay. Now we move on to the most important step, which is the training. So in this step, in this particular part of the code, we will be training the simple perceptron on the OR logic. Okay, how do we do that? We'll be so we will set two loops. Okay, one is the outer loop and one is the inner loop. Okay, so the outer loop is for epoch in range 10. Okay, so we are introducing a new term epoch. Okay, so epoch, I tell my students is that epoch is simply how many times we are hitting the perceptron. Okay. So suppose we give some input to a perceptron. Okay, and it gives us the prediction based on that input. Okay. But the prediction was incorrect. Okay. So we hit that perceptron. Okay. We say no, the target was this. You have predicted this. So you need to make some changes. You need to update the weights and biases. Okay. So I'm hitting the perceptron until it makes the correct prediction. Okay. So here we have set the range for epoch as 10. So we'll be hitting the perceptron 10 times. Okay. So this is the outer loop, then the inner loop. Okay. For I in range. Okay. So here what we are doing is we are simply assigning the inputs, and we are saying that the output will be the target. Okay. So target is yi. Okay. So target is 0 1 1 1. Okay, the inputs are 0 0 0 1 1 0 and 1 1. Okay, so we are here just simply saying in the inner loop that we have assigned the inputs and we have set a target. Okay, then we ask the perceptron to make the prediction. Okay, how do we make the prediction? I'm pretty sure you already know the formula for weighted sum. So weighted sum is input multiplied by weights plus bias. So in this case, we'll have, since we have two inputs, x1 and x2, we say x1 multiplied by w1 plus x2 multiplied by w2 plus bias. Okay. So here we have just simply said weighted sum is equal to dot product of inputs and weights plus some kind of bias. All right. Then after calculating the weighted sum, we we use a simple logic. Okay, that is how the perceptron will make the prediction. We say if the calculated weighted sum came out to be greater than 0, then the prediction will be 1. In all the other cases, it will be 0. Okay. Now suppose after calculating the weighted sum, it came out to be, suppose it came out to be 2. Okay. So 2 is greater than 0. So prediction will be 1. Okay. Now suppose the weighted sum came out to be minus 1 or minus 2 something. Okay. Then the weighted sum is less than 0. So the prediction will be 0. So this is a very simple logic which we have used for making the prediction. Okay. Then, okay, so after that, we'll calculate the error. Okay, now we already know what the target is. Target is supposed to be 0, 1, 1, 1. Okay, so first iteration, it will be 0, second, 1, third, 1, and fourth, 1. Okay, so target we already know that which we have to train the perceptron on. Prediction will be calculated in this step. So we will calculate the error. Okay, so this is how we make prediction. And then after that, we can just print what is the prediction, what was the correct target, and what was the error. Okay. You cannot open this file. I think you are opening this in Google Drive. Okay. So what you have to do is you have to search Google Colab. Okay. So in the browser, you say Google Colab. Okay. And then after opening the Google Colab and you can sign in, I have already signed in. You go on File, you go on Upload Notebook, and then browse. Okay, and then you open the files that I have shared with you. So if I open this, so it will be uploaded. Okay, and then it will open like this. Okay, so try it this way. Don't open it on Google Drive. If you open it on Google Drive, you have to open it in Colab, Google Colab. So everyone, were you able to open the coding file? Were you able to do it?
Yes.
Okay, okay. All right. So we have made the prediction. We have printed what the prediction is, what is the correct target, what is the error. So it will basically show us for every iteration what the prediction is, what the correct target is, what the error is. Okay. Now, as I said earlier, what a simple perceptron does is we give it some kind of target. Here in this case, we have give the target as 0, 1, 1, 1, right? And it will compare that target with the prediction that it has made. Okay, using the weighted sum and this logic. Correct? And then it will calculate the error. If there is error, if there is error, then we update the weights and biases using this formula. This you have to learn because there's there's mathematical logic behind it, but this you have to learn. Okay. So if the perceptron encounters an error, we update the weights and biases. How do we do that? We say the new weight will be equals to the original weight, which was 0 as we have initialized with 0. So the new weight equals to 0 plus learning rate, which we have set as 0.1 multiplied by error. So error will be calculated in this line multiplied by inputs. Okay, so inputs in the first iteration will be 0, 0. Okay, second iteration it will be 0, 1. Third it will be 1, 0, and then finally 1, 1. Okay. So this is how we update the weight. And for the bias, we say new bias equals to the original bias. Original bias was 0, since we have initialized the bias with 0, multiplied by learning rate, which is 0.1, multiplied by error. Okay. So in case a perceptron encounters an error, we'll be updating the weights and biases using this formula. And then again, we will calculate the weighted sum. We will let the perceptron make a prediction. Then we will check it with the target. If there is an error, then again we update the weights and biases. Okay, we will keep on doing that until we receive no error. That is, the target and prediction will be the same. Okay, so this is how we train a simple perceptron. Okay, so let us run this. So you can see it has showed all the calculation for every iteration. Okay, so for every iteration for epoch number one, inputs are 0, 0. The prediction came out to be 0. The target was 0, so there is no error. So updated weights and biases there will be no update in weights and biases. So we say 0, 0. Okay. Then again for the next iteration, the input will be 0, 1. Then it will calculate the prediction. But the prediction came out to be 0, but the target was 1. So there is one error. Okay. So then we will be updating weights and biases using this formula. Okay. So this is how we train a perceptron. Okay. So as you can see for epoch 1, it has 4 cases. Then epoch 2 again 4 cases. Epoch 3, epoch 4. Okay. Until epoch 10. And epoch 10, you can see uh, that for epoch 10, the error for all the 4 cases for 0, 0, 0, 1, 1, 0, 1, 1, it came out to be 0. Error 0, error 0, 0, 0. So it means at this point, we have achieved convergence. We have achieved the successful training of the perceptron on the OR logic. Okay. So how do we test it? So using this, we will again calculate the weighted sum. After training the perceptron, we will calculate the weighted sum using the dot products of inputs and weights plus bias. Okay. Then we will ask the perceptron that we have already trained on 10 epochs to make a prediction. Okay. And then we will print the input and prediction. And as you can see for 0, 0, the prediction is 0 and the target was also 0. For 0, 1, the prediction came out to be 1, target was also 1. For 1, 0, the prediction came out to be 1, the target was also 1. For 1, 1, the target was also 1 and the prediction came out to be 1. So that means at this point, after 10 epochs, the model is successfully trained on the OR logic. Okay, so this is simply how we train the OR logic. We train the perceptron on the OR logic. Okay. Now suppose we want to train uh, it on AND logic. Okay. So we have different types of AND and OR gates, right? AND gate, OR gates, NOR gate, NAND gate, XOR gates. We have so many gates. Okay. So let's try the AND gate as well. Okay. So for the AND gate, now for the AND gate, our target is supposed to be okay. So for the AND gate, the target is supposed to be for 0, 0, it should be 0. For 0, 1, it should also be 0. Now we are doing the AND gate, okay? So 0, 0, it should be 0. So 0, 1, it should also be 0. For 1, 0, it should also be 0. And for 1, 1, it should be 1. So this is the AND gate, okay? So this is how AND gate behaves, okay? So so all we have to do is that we have to change this part of the code. Okay. So in this part, we have initialized the inputs and the output for OR gate. So we just change it for the AND gate. What we say is for 0, 0, it should be 0. For 0, 1, it should be 0. So we change it to 0. For 1, 0, it should also be 0. So we change the 1 to 0. And for 1, 1, it should be 1. Okay. So this is a very simple change that we have to do in order to implement the AND gate. Okay, then we run this. Okay, this will be the same because every time we initialize the weights and biases with 0. Whenever we are training a simple perceptron, we'll be initializing it with 0, 0. So we have initialized the weights, we have initialized the bias as 0. We have set a learning rate. This you can do anything 0 0.1, 0 0.2, whatever you want. Then the training loop. Okay, training loop will be the same. We are training this perceptron on 10 epochs. That means we are hitting the perceptron 10 times, okay, this all will be the same, okay. So as you can see over here, for every epoch, it has showed us the calculation, what is the prediction, what is the updated weights, what was the target, what was the error, everything, okay. So as you can see on the 10th epoch, you can see for 00 error is 0, for 0 1 input error is also 0, for 10 input error is 0, for 11 it is 0. So that means after 10 epochs, our perceptron has been trained on the AND logic, okay. How do we check that? We test the trained model, okay. We test it and we can see for input 00 the prediction came out to be 0. For 01 prediction came out to be 0 and the target was also 0. For 10 the prediction came out to be 0 and the target was also 0. For the input 11 the target was 1 and the prediction came out to be 1. So it means after 10 epochs we have trained the simple perceptron on both the and the OR logic. Why do I get error when I run? Uh, why are you getting the error? You're getting the error in the inner loop. You may be getting the error because you might not have run all the line of codes. Okay, so you have to run first this, then this, then this, and then this. So if you directly run this without running all these, then you will get an error in this because ultimately we are using Python, right? So we are doing it line by line. So we run this first, and then this, and then this, and then this. Okay, try this and let me know. Okay, so uh, we have trained a simple perceptron on OR and AND logic. Okay, so is this clear? Any questions in this, guys? Clear. Okay. 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 All right. So now, so now what we'll be doing is we'll be implementing XOR logic. Okay. Let's see what XOR logic says. Okay. So XOR logic, we say for 00 the output should be 0. For 01 the output should be 1. For 10 the output should be 1. And for 11 it should be 0. So this is the XOR logic. Okay. Now we have to train this logic. Um, okay. How do we do that? As I said, let's try to do, okay, we did OR gate, we did AND gate, right? Okay, so according to what I told you, it should be for 00. We just have to make changes over here, right? So for 00, it should be 0. So we say 0, okay? For 01, it should be 1. So we say 1, okay? For 10, for 10, it should be 1. So we make the change here, 1. And for 11, it should be 0, okay? It should be 0. So all we had to make a change over here, just like this, okay? So we run it. Then again, the same steps, initialize the weights and biases. We run this as well. Then we run the training loop, this simple. And then we check the train model, okay? Now, as you can see over here, for input 00, the prediction that our perceptron is giving, it is 1, okay? But the target was 0, right? For 01, it is giving 1. Target was also 1. Okay, so for this part, it is right. For the third iteration, for 10, the prediction is coming out to be 0, but it is supposed to be 1. So it means that the XOR logic after 10 epochs has not been trained. Okay, so let's try using 20 epochs. Okay, let's see what happens. Maybe run it again. okay, and then we test it. Still the wrong predictions, right? So what is happening? Okay, why is it not predicting? Why is it not predicting like AND and OR gate? So the logic behind uh, that this perceptron is giving the wrong prediction is because see it this way. Okay, let's go back to the OR gate. Okay, and let's try to visualize the OR gate on a 2D plane. Okay, so on a 2D plane for 0 0. Now we are talking about OR. Okay, for 0 0, the output should be 0. Okay, so we say red dot for 0 and blue dot for 1. Okay, so for 0 0, the OR gate should give us 0. Okay, so red dot is 0. Correct? Now we are visualizing uh, OR logic on a 2D plane. Okay, for 0 1, for 0 1, for OR gate, it should be the output should be 1. So we say 1 or blue dot. Okay, for 1 0. For 1 0, the output should be 1. Okay, so blue dot again. And for 1 1, for 1 1, output should be 1. This is the OR logic, right? So what a perceptron does is when we are training a perceptron, it draws a line between it draws a line on this 2D plane, okay? How does it do that? It draws a line on this 2D plane such that all the ones are on one side and all the zeros are on one side. So it draws a line like this, okay? So that all the blue dots or the ones are on one side of that line and all the red or the zeros are on the other side, okay? And that's how it makes the decision, okay? By drawing a line. Okay, so this is OR. Now for XOR logic, the problem is now for XOR, I have already implemented 0 is here, 1 is here, 0 is here, and 1 is here, okay? For 0 0, it should be 0. For 0 1, it should be 1. For 1 0, it should be 1. And for 1 1, it should be 0. So here, as you can see, now we are implementing the XOR logic. We are visualizing the XOR logic, okay? You cannot draw a single line such that one are on one side and zeros are on the other side. Can you draw a line? You cannot draw it like that. You cannot draw it like that. You cannot draw it like that, nor like that, okay? So whatever you do, if you draw a single line, you cannot separate this space such that ones are on one side and zeros are on the other. So this is why we cannot train the XOR logic using a simple perceptron because the XOR input space is linearly inseparable. That is, we cannot draw a line to separate such that zeros are on one side and one on the other. Okay. So how do we implement XOR logic? Okay, we cannot implement it using a simple perceptron. So that's where multi-layered perceptron comes into place. Okay, and now we will be coding that multi-layered perceptron so that we can implement the XOR logic. Okay, and we will be using back propagation to train this perceptron. Okay, okay. So let me show you a little bit. Uh, Let me show you the structure of a perceptron, of a simple perceptron and a multi-layered perceptron. Okay, so okay, Okay, so this is basically a simple perceptron, right? We have the two inputs x1 and x2. We have attached the weights 1 and weight 2 to the inputs, and we will add another bias to it, bias to it, and then we get the output. Okay, so this is basically a simple perceptron, right? This is the structure of a simple perceptron. Okay, now the change that we have to do in a multi-layered perceptron is that we introduce in between the inputs and the output, we introduce another layer. Okay, how do we do that? We we say, so what do? We introduce a hidden layer in between the inputs and the outputs in a multi-layered perceptron. Okay, so uh, we have okay. So what do we have here? We have input x1, input x2. Okay, then we have another layer, which is the hidden layer. So we say hidden h1. Okay, and hidden neuron 2 h2. Okay, and then we also have some weights. We have w1, w2, w3, w4, w5, w6. Okay, and then finally we have the output y. Okay, so this is a multi-layered perceptron. Okay, this is the structure of a multi-layered perceptron. This is of one hidden layer. Okay, we can introduce however many hidden layers. Okay, here we have one hidden layer. We can introduce two hidden layers. For implementing the XOR logic, we need only one hidden layer. Okay, so we introduce one hidden layer and two hidden neurons, H1 and H2. Okay, so and we also introduce some weights to it. Okay, so there are four weights W1, W2, W3, W4 between the input layer and the hidden layer. Okay, and then we have another two weights W5 and W6 between the hidden layer and the output layer. Okay, so this is the basic structural difference between a simple perceptron and a multi-layered perceptron. Okay, okay, now let's implement the XOR logic. So the step number one, import the NumPy library. Same as the previous one, right? So because we are performing some mathematical function, we need the NumPy library. Okay, so we run this. Okay, so the library is imported. Okay, now we are teaching the model, this multi-layered perceptron, on the XOR logic. So for XOR logic, for 0, 0, it should be 0, for 0, 1, it should be 1, for 1, 0, it should be 1, and for 1, 1, it should be 0. Okay, so step number 1 is just defining the arrays. Okay, similarly, how we did it over here, we have initialized the input array and the output array. We have done it over here as well. We have initialized the input array and output array. So input 0, 0, 0, 1, 1, 0, 1, 1, and the output 0, 1, 1, 0. Simple. So we have defined what logic we have to train our perceptron on. Okay, and we run it. Okay, after that, we define an activation function. Okay, so this is the difference between um, a simple perceptron and a multi-layered perceptron. Okay, so in case of simple perceptron, what we used to do is that there is a function. Usually, it is a linear function. Okay, and in brackets, there was weighted sum. Weighted sum. Okay, so this is how we used to calculate. We used to calculate the weighted sum and then uh, use a linear function on it. Okay, but in case of multi-layered perceptron, we'll be using a sigmoid function. Instead of a linear function, we'll be using a sigmoid function. Okay, and the sigmoid function is basically sigmoid function. So sigmoid function and the weighted sum. Okay, now because here, since it is a complex case, so a linear function, as I told you, that a linear function cannot divide the XOR such that zeros are on one side and one on the other. So we'll be using a more complex function, which is the sigmoid function. Okay. So in this part of this code, we are just defining what a sigmoid function is. Okay. So a sigmoid function by mathematical definition is calculated as 1 upon 1 plus e to the power minus x. Okay. So this is the formula for a sigmoid function. Okay, so this again you have to learn what is the formula for sigmoid function and you define it in this part of the code. Okay, so the sigmoid is 1 upon 1 plus e to the power minus x. Okay, so just you in this part you have defined the sigmoid function. Okay, and then we will also be calculating the sigmoid derivative. Okay, so derivative, why do we calculate derivative? Because in this case, since it is a complex case, it is a multi-layered perceptron. Sigmoid derivative, the derivative of the sigmoid function is, it will tell us how to update the weights and biases. Okay. Earlier we used to update the weight and biases using this simple formula, right? In this case, we'll be using a sigmoid derivative to update the weights and biases. Okay. So this is just defining the functions. So we run it. Okay. And after that, we will initialize the weights and biases. Now, I already told you that in case of simple perceptron, we initialize the weights and biases with 0. Okay. But since this is a multi-layered perceptron, what we'll be doing is that we'll be assigning random values to it. Okay. We say we don't initialize with 0. We say we ask the Python programming language that assign just a random value. Okay. Do not initialize with 0, just assign a random value. Okay. So in this case, what we are doing here is that firstly, we'll be using random value. Okay. So first, the input layer neurons are two. As you can see in this diagram, the input layer neurons are two, x1 and x2. Okay. So we are just saying the input layers in this particular network, the input layer neurons are two. Hidden layer neurons are also two. So the hidden layer neurons are h1 and h2, two. And the output neuron is one. So output neuron is 1. Okay, so in this part we are just saying, okay, if we need more than if we need 4 hidden neurons, so we say 4 over here. Okay, in complex cases. Okay, this is up to the use case, okay, what we are trying to, what logic we are trying to train the perceptron on, okay. So in this case, input layer neurons are 2, hidden layer neurons are 2, output neurons is 1, okay. Then we assign random values to the hidden weights, okay. So the hidden weights, we assign all these W1, W2, W3, W4, we assign random values, okay. So in this part, we are just assigning random uniform values, okay. So suppose the first random value that we assign is 1 and the second is 2, okay. Then the third is supposed to be 3 because we are doing it uniformly, okay. So this is just assigning hidden weights with random values. Hidden weights W1, W2, W3, W4, random values. Okay. Then the hidden bias, another random value. Okay. We give it a random value again. For the output weights, for W5 and W6, another random values. Okay. So NP random dot uniform. Okay. And for the output bias, also random value. So in this particular part, we have just assigned the random values to the weights and biases. Okay. And then we run this. Okay. Now training the network. Okay, we have initialized the weights, we have defined what logic we have to train the perceptron on, we have defined the activation function. Now we will train the network. Okay, okay. Now let's train the network on one epoch only. Let's see what happens if we train it only on one epoch. Okay, okay. So for that, how do we train it? Okay. Now this is where a difference comes in. Okay, in case of multi-layered perceptron. So how do we do that? Firstly, we will do a forward pass. Now, forward pass, I will tell you, it is basically when we are calculating the output using the inputs, we are calculating the weighted sum and we are attaching a function to it. Okay. So a forward pass is simply, in this case, so how do we calculate the weighted sum? We say x1 multiplied by dot product of w1 plus x2 multiplied by w3, x2 dot product w3, okay, plus some bias, okay. So for this particular case, and then we attach a sigmoid function to it as well. This is sigmoid function to, okay. So this will be the input for the hidden layer number one, okay. And similarly, for the input of hidden layer number two, for the hidden layer number two, it will be x2 x2 dot product of the weight w4 x2 multiplied by weight plus x1 multiplied by weight. So x1 w2, okay, plus some kind of bias and attached with is a sigmoid function. Okay, so this will be the input for hidden layer neuron 2. Okay, this will be the input for hidden layer neuron 1 and this will be the input for hidden layer neuron 2. And then again this we will multiply with weight 6 and this will multiply it with weight 5. We will attach a bias to it, then again a sigmoid function, and then we calculate the y. Okay, so this is what we call a forward pass. Why do we call it a forward pass? Because we are moving from the input to the output in a forward way. Okay, so first we are calculating we are taking x1 and x2. We are calculating the weighted sum attached with the sigmoid function. That the result of that we will be taking input for h1 and h2. Then we'll multiply it again with w5 and w6 plus add some bias to it, and then the sigmoid function, and the result of that will be the output. So we are moving in a forward way. Okay, so we are doing the calculation this way. So this is what we are doing over here as well. So we are calculating the forward pass. How do we do that? Hidden layer input equals to dot product of the input and the hidden weights plus hidden bias. Okay, so dot product of inputs with the hidden weights, okay, plus some kind of bias. Okay, so in this line we are doing this calculation, and then we attach a sigmoid function to it as well. Okay, and again for final input and final output, we will be taking the dot product of hidden layer output multiplied by output weights. So the output of hidden layers multiplied by the output weights will be the result, will be the output. Okay, so this we are doing, and then we are attaching a sigmoid function to it. Okay, so this is just this calculation that I showed you over here. Then now, okay, we have done a forward pass. Then the next step is back propagation. Okay, back propagation is something that will be updating the weights and biases on. Okay, how do we do that? Now, for OR gate, the formula was very simple, right? This was the formula. For a multi-layer perceptron, we use backpropagation, okay? And this is again, this is something that you will have to learn because this is a formula, okay? Just like this was the formula and you have to learn, this is again a formula that you will have to learn, okay? So we calculate the error as outputs. So outputs which were supposed to be 0, 1, 1, 0 minus the final output, which is what the perceptron has predicted, okay? So this, after all this calculation, after the forward pass, it will our perceptron will give a final output, okay? And the outputs which are the targets, okay, which are supposed to be the target 0, 1, 1, 0, okay, and we calculate the error, okay. Then we calculate the derivative of the output using this formula, okay. So we say derivative of the output equals to error multiplied by sigma derivative of the final output, okay. So this is again a formula, okay. We calculate the error and we calculate the derivative of the output. Why do we need the derivative of the output? As I said earlier, we need a sigma derivative so that we can update the weights and biases accordingly. Okay, so that's why we are calculating the derivative of the output. Okay, similarly, we calculate the error of the hidden layer. Okay, now in this particular part, we have calculated the error for this part. Okay, we will also calculate the error for this part as well, for the hidden layer as well, using simply this formula dot product, okay, of the derivative of the outputs and the output weights, and T is basically a transpose. Since we are dealing here with arrays, so we have to take a transpose so that the output is in the same format as we have given the input. Okay, so this is why we have used the transpose matrix over here. Okay, then we have to calculate the derivative of the hidden error. Okay, so using this formula. Okay, this part you will have to learn because this is mathematical formula and this is not. Okay, it is logic, but it is mathematical logic. Okay, so you have to learn. Okay, then again, after calculating the error, the derivative of the output, the hidden layer error, and the derivative of hidden output, we update the weight and biases using this formula. Okay, so output weight equals to hidden layer output dot product of transpose dot product of the derivative of the output that we have calculated multiplied by learning rate. Okay, so this is how we update the output weights, then output bias. We take the sum of all these multiplied by learning rate. Then again hidden weights like this and hidden bias like this. Okay, so from this to this all logics you have to learn because these are all formulas. Okay, okay, so this is how we update the weights and biases. And let's train a perceptron on only one epoch. Let's see what happens. Okay, we train it on one epoch, okay, and let's see what happens. Let's see what the output is. Now, as you can see, the output is coming out to be 0.86, 0.878, 0.88, 0.891. Correct? But the supposed target was 0.110, right? Even if we round it, uh, we will get, even if we round it, what we'll get is we'll get 1111. Correct? This means that after one epoch, the perceptron is not trained. Okay. So what do we say? We say, okay, let's try it for 10 epochs. Okay. And then we run the whole program again. Okay. Let's do it for 10 epochs now. Okay. And let's see what the results are. Again, 0.8, 0.837, 0.84, 0.852. Still, the network is not trained. Okay. Let's try for 100 epochs. So we say 100. Again, again for 100 epochs. Let's see. Okay, now it is 0.5, 0.5, 0.5, 0.5. Still not what we were supposed to get. We were supposed to get 0.111. Okay, so still not there. Okay, let's try 1000 epochs. Let's run it again. Now for 1000 epochs and 0.4, 0.5, 0.5, 0.5. Still not. Okay, okay, then again for 10,000 epochs. Let's see what happens. Okay, now we are getting closer. You can see for the first one, it is getting 0.058, so which is closer to 0. For the second, it is 0.947, which is closer to 1. Then again 0.947, which is again closer to 1. And then 0.057, which is closer to 0. Okay, so okay, we are getting there. Let's try it for 100,000 epochs. Okay. Now this will take some time because 100,000 epochs is a lot. Okay, now it is taking some time because we are dealing with 100,000 epochs. It took 5 seconds. Then let's see what happens after 100,000 epochs. Now, as you can see, the zeros are getting closer to zero. So it is getting closer to zero, 0.013. Zero, and this is getting closer to 1, 0.989, 0.989, 0.011. Okay. So the more epochs we train on, okay, let's try uh, a million. Okay. Let's train it for a million epochs. Okay, let's see what happens. Now this will take a lot of time, I think. 1 million epochs. And you can see this green arrow, this is how it is training. Okay, this is how it is training. First it is doing the forward pass, then it is calculating the back propagation, then it is calculating the updated weights and biases. Okay, so this is taking a lot of time since it is a 1 million epochs. Okay, still taking time. Okay, still executing 39 seconds. Okay, okay, done. So it took 54 seconds to execute this particular part of the code, and let's see what the outputs are. Okay, now we are almost there. So this is 0, almost 0. This is almost 1. This is almost 1, and this is almost 0. Okay. So the point. here is that the more we train a perceptron on, the more epochs we train it on, the better result we will get. Okay. After this is 1 million epochs, this is what we are getting. Okay. If we do it 10 million times, of course my laptop cannot do it. Okay. Uh, the result will be even better. Okay. So the more you train the perceptron on, the higher or the correct the output will be. Okay. So this is how we implement XOR logic. So any questions? Any questions, guys? Is it clear? Okay. Okay. So why do we introduce hidden layer? So this is okay. So this was the XOR input space, right? One were on the one sides, opposite sides, and zeros were on the opposite side. So why do we introduce hidden layer? So I will show you that. So after adding a hidden layer, after adding a hidden layer, the ones are on one side and the zeros are on the other side. So this is why hidden layer is important. It transforms the input space such that ones are on one side. So this is actually two ones. It is overlapping. So we have two ones over here and we have zeros over here. Okay. Now it is separable. So this is why hidden layers are important. It lets us transform the input space such that zeros are on one side and one on the other. That is why hidden layer is important. So this is how we train the XOR logic, guys. And I have shared both these codes with you guys. If you have any question, then you can ask. Otherwise, it is time. Is it 2 hours or 1 hour? The class. Is it supposed to be 1 hour or 2 hours?
2.
2 hours. Okay. So we are done. And so it took us only 1 hour. So this you can implement it yourself. I have shared the codes with you. Try to see how all this logic is done. Okay, try it on your own. Maybe okay. So now suppose for 1 million epoch, now I am here using, as you can see, I am using um, my own laptop's resources over here. So my system RAM is actually 16, but the available RAM is 12.7 only. Okay, so and this is the storage. Okay, this storage. Okay, now suppose you are not able to, we have to train it on even more epochs. Okay, so what you can do is you can use the Google resources. How you can do that? You can select runtime. Okay, then you can change the runtime type. Okay, you click on it. In this particular case, I'm using my own CPU. Okay, now it is using my own laptop's RAM and my own laptop's disk storage. Okay, now we have Google resources. So Google has this Tensor 4 GPU and this TPU. So these are much faster than my CPU's RAM. Okay. So if you want to implement the 10 million epochs, you can select on any of these. Okay. You can, now I'm running two. So you can, if you can cut this, then it will let you select this one. Okay. And you can select this and then you can select on save and then you can try it one more time. Okay. Now since there are two active sessions, so it will only allow for one session. So you can close the other one and you can use the another Google resources. Okay, so which is faster than our own laptop. Okay, so this is how you can do this. Okay guys, so that's it. If you have any questions, then you can ask. Otherwise, that's it for the class. Any questions? No
No.
questions? No questions. Okay. Okay, then try it on your own, guys. Okay. So that's it from me. And if you have any questions even later after the class, you can just text me, okay? Let me write my number over here. So if you get any question, if you have any problem with the code, you can just text me on Telegram or on WhatsApp, whatever you want, okay? So guys, that's it. Thank you very much and have a nice day. Assalamu alaikum.
Thank you.
Thank you, sir. Thank you, sir.